Welcome back. In this section, we'll be talking about properties of logarithmic functions. And these are properties that we'll need to use if we want to be able to solve a logarithmic equation. We'll need to be able to manipulate our logarithms, so we need to know some of these properties. The ones on this slide are all really properties that emerge from the fact that a to the power of x and log base a of x, that those are inverses of each other. So for the first two properties, these are really just the things that we know about the graph of our logarithmic functions and our exponential functions. You know on an exponential function, a to the power of 1 is a, or in other words, on the graph of an exponential function, you have the point 1a. If 1 is the input, a is the output. But of course that means for a logarithm you should have the opposite. You should have that if a is the input, 1 is the output. Or in other words, log base a of a is equal to 1. And similarly, we know that anything to the power of 0 is equal to 1, or on the graph of an exponential function, you'd have the point 0, 1, which means on a logarithm, the graph of it, you should have the point 1, 0. Or for logs, log base a of 1 is equal to 0. The other two properties, again, come from what we know of inverse functions. Remember that if you have a function and its inverse, then f composed with f inverse should give you x, and f inverse composed with f should give you x. So in terms of logarithms and exponential functions, that means that if you put an exponential function inside of a logarithm, or put a logarithm inside of an exponential function, they will undo each other, and what you'll have will just be x. We also have some properties that are similar to the properties that we had for exponents. So if you'll remember some properties like if you had two exponential expressions with the same base and you multiplied them together, you would add the exponents. And we also knew that if you had two exponential expressions with the same base and you divided them, that would just be the difference in those powers. We have similar sorts of properties here for logarithms. If you have a log of a product, that's log of that first factor plus log of that second factor. If you have log of a quotient, that's log of the numerator minus the log of the denominator. So notice there's similar properties. There's a relationship between division and subtraction, but they're not exactly the same. The other properties that we have a very useful one. This is when we have log of something to a power. This property is that if you have log of something to a power, that power can come down in front. So, in other words, if you had something like log base 3 of 2 to the power of 4, that could be rewritten as 4 times log base 3 of 2. In a sense, it's related to that property that we had of powers to powers, that when something, an exponential function is being raised to a power, that you multiply things together. So in this case, multiply the powers. In the case of the logarithm, we're multiplying the power and the logarithm together. So again, similar properties, but not the same. The last property that we have is a very useful one. If you have two logarithms, both with the same base, and they're equal to each other, so if log base a of m and log base a of n, if they're equal to each other, you can conclude that m and n, what's inside those logs, have to be equal to each other. And the reason why we know that this is true is because logarithms are one-to-one functions. When I say this, what I'm really saying is if you had a function, log base a of x, then these would be the outputs of that function. And we're saying we have two y values that are the same. Well, then the x values that got you there must be the same. Because remember, for a one-to-one function, if the y values are the same, then that means that the x values must be the same as well. And we know logarithms are one-to-one functions, and so that's how we know that if you have log of base a of something equals log base a of something else, that those two somethings must be equal to each other. All right, so we're going to do some evaluating here, and as usual, evaluating without our calculator. In the case of A, we can evaluate this by hand, nicely and easily, using a couple of our properties. So to start off with, the first property that I'll use is that when I have natural log of something to a power, that you could say that that power comes in front. So that's 2 natural log of e plus natural log of 1. The next part that we know is that since it's a natural log, and natural logs are log base e, then that means that for natural log of e, that is log base e of e, that should be equal to 1. And that's using our very first property that we had, that log base a of a is always equal to 1. Here in this case, the base is e, so log base e of e is equal to 1. The other property that we had was log base anything of 1 is always equal to 0. So natural log of 1, that should be 0. And now we have on the left side, it's equal to 2 for that first example. So natural log of e squared plus natural log of 1, that's 2. For the example in B, we can't evaluate these logs just yet, because if you try to evaluate any of these, you'd have to ask yourself things like 8 to what power gives you 6, or 8 to what power gives you 4, or 8 to what power gives you 3. And those are all questions that I don't have easy answers to. But if I use some of the properties that I know of logarithms, I can combine these. Namely, you have one log plus another with the same base. That's log base 8 of the first times the second, or of 6 times 4, which is 24. Now I've got log base 8 of 24 minus log base 8 of 3, and that's log base 8 of 24 divided by 3. And 24 divided by 3, of course, that's just 8. Now I can evaluate this. I have log base 8 of 8, and I know that just like it was for natural log of e, that was equal to 1. That was log base e of e equal to 1. Similarly, log base 8 of 8 is equal to 1. All right, something that we might have to do is to take a logarithm and split it apart, or take a bunch of logarithms and put them back together as a single logarithm. So here's a little bit of practice doing this. We have one big logarithmic expression, and we want to rewrite it as a sum or difference of logs. So we want to split it up as a log plus another log, maybe plus another log, maybe minus a log. Also, we want to make sure that if there's any powers, that we've brought them down in front as factors. So the first thing that I'll do, I have log base 2 of a fraction, so that's log base 2 of the numerator minus log base 2 of the denominator. So I'll have log base 2 of cube root of x times x minus 1 cubed minus log base 2 of x plus 2 to the 4. Next, I'm going to take the first log that I have here. I have, again, log base 2 of a product in this case, cube root of x and x minus 1 cubed. I know that that can be split into two logs added together. Log base 2 of cube root of x. And cube root of x, I'm actually going to rewrite that as x to the power of 1/3. And then plus log base 2 of x minus 1 cubed. I rewrote it as x to the power of 1/3 because I know that my ultimate last step here will be to bring down all of the powers in front as factors, And I know that cube root is really a power, so I rewrote it as a power so that I can do this. Log base 2 of x to the power of a third is 1/3 log base 2 of x. And the next one, log base 2 of x minus 1 cubed, that's 3 log base 2 of x minus 1. And the last one, minus 4 log base 2 of x plus 2. All right, so there we go. We've split up our logs as much as we possibly can. They can't be split up any further. One thing just to note here, as far as properties of logs go, we don't have any way to split up a log where it's two things that are subtracted from each other or two things that are added to each other. So something like log base 2 of x plus 2, that can't be split up any further. A lot of people would like it to be possible for me to split this into a log base 2 of x and a log base 2 of 2, except unfortunately, no, we cannot do that. One other little warning that I have to give about this business of bringing the power down in front, that only is possible when it's the entire of what's going inside the log being raised to that power. So here I had x minus 1 cubed. The entire inside of the log was being cubed, so the cube was able to be brought down in front. Compare and contrast that with something like log base 2 of x cubed plus 1. In that case, the cubed, you would not be able to bring that in front because it's not a power on the entire inside of the log, it's only a power on the x. So something like this expression, the power, you would not be able to move it in front. So we just have to be a little bit careful here when we're moving powers in front. That's only if the power is on the entire inside of the logarithm. So here the 4 was on all of the x plus 2, so the 4 was able to be brought in front. Similarly with the 3, and similarly with the 1/3. All right, so let's do the reverse now, rewriting this as a single logarithm. And so we're going to basically do the steps that we did before in reverse, bringing first our powers up. And then once we do that, we'll have a bunch of logs that are either being subtracted or added from each other. So we'll be able to then put them together as one single log. So starting off, we have log of 3 squared minus log of x plus 2 cubed plus log of x minus 1 to the half. One thing just to mention before I do anything further, and that's, you'll notice these logs don't have a base, and that's because they're common logs. They're really log base 10. Remember that when we don't see a base on a logarithm, it's a log base 10. So what do we have? We have log of 9 minus log of x plus 2 cubed plus log of, I'm going to rewrite this as a square root. And now I can start putting things together. I know that when you have one log plus another log, then it's 2 logs. Those 2 logs could be combined together as one log, where the inside is just that product of those 2 things. So we would have log of 9 times the square root of x minus 1. And then we have one log minus another log. That becomes the log of a quotient. Log of 9 root x minus 1 all over x plus 2 cubed. Now, I did say that for the most part, we're not going to be interested in finding approximate values for things that usually we leave exact values only. But there are some cases where we have some applications where we might want to know our answer as a decimal number. And so that means we'll need to be able to evaluate any log, find the approximate value using our calculators. Now, as you know, our calculator only has two different log functions. There's log base 10 and log base e, the natural log. Now, the reason why we only have these two buttons is because there is a change of base formula that allows us to change our log from any base that we have into any other valid base. So here, when we're talking about the bases, of course, they have to be positive. The bases can't be 1, that's the other little restriction. And of course, whatever log we're talking about, the thing that's going inside the log has to be positive as well. But the idea of the change of base formula is if you have log base a of anything, and you want to switch it to another base, base k, well, that's log base k of what was originally inside the log over log base k of the original base. So if you were looking at something like log base 4 of 72 and you wanted to come up with the approximate value, you could choose to rewrite it as any other base, but since our calculator has log base e and log base 10, it makes sense to use one of those. So I could rewrite it either as log base 10 of 72 over log base 10 of 4, or I could rewrite it as natural log of 72 over natural log of 4. And you can confirm that both of these are actually equal to each other. And they're both equal to approximately 3.08496 and so on. So if we rounded it off to 4 decimal places, that would be 3.0850.